He hasn't been there.
All right, let's go ahead and look at what to expect on test 5 here. We got the chapter 20 think well material, but then my additional stuff with the conic section. So worksheets 10.1 through 10.5, and 10.1, that was my additional stuff with the conic sections. Two basic problems from that. Here's some information about the conic section. What is the equation? Or here's the equation. Give me the details of what's the vertices, what's the center, or the vertex on case of the parabola. So those basic types. Parabola, we'll just kind of look at the basic forms. Formula for that is what?
X minus h over.
Nope, parabola.
Squared. Plus equals 11. Like I said all along.
Yeah, the parabola kind of goes away from the others. The others are very similar, but parabola here, this would be, well, we're used to the parabola a little bit more. Y equals x squared. That opens up, so this form would open up or down, and it opens up if P is positive, opens down if P is negative. Okay, so that's all determined by the sign of P. And then the other one, if we're squaring the y part, okay. Now, you are allowed one sheet of paper again, so.
Yay. Amazing.
So your typical 8.5 by 11,
You have to
8.5 inches by 11 inches.
you have to multiply by 2 because it's calc 2. So
Oh, well, front and back. So,
yes.
there you go.
Math. Yay.
So this would open right if P is positive, and left if P is negative. And the key part to the parabola, the vertex, is your HK, and then also the focus. In the parabola, it has just one focus. In the hyperbola and the ellipse, they have two focuses. No, foci. Foci. I've heard it pronounced both ways. But
The directrix, which one is it?
directrix is with the parabola.
It's
so
it's P, the P value, right?
Yeah. From the vertex to get to the focus, that's the go from the vertex a distance, a directed distance of P. So if P is negative, then you'd go either down or left to get to the focus. And then you go the opposite direction to get to the directrix. So, okay. Questions on the parabola? Okay, for the ellipse, we'll have this equation, this formula, and this will give us a horizontal major axis. The ellipse will be like that. And we know that because of what?
The X and Y.
The signs right, the negative.
No. No.
Oh, A and B?
Okay, the A and the B. A is always greater than B for the ellipse. So whichever one of these is larger, that will determine, in this case we're showing it under the x, so that will determine the major axis. If we have this, now it's hard to show with just the letters, but if the denominator of the y part is larger, then we'll have the vertical major axis.
What if it equals 0? Like the whole equation still equals.
Okay. Yeah, if that's a case, if we end up with equaling 0, that's one of those degenerate conic sections. I won't have anything like that on the test, but that's one of those kind of special cases that we're not going to worry about. It's basically just ends up being a point. So, well, again, center, HK is your center. So that's going to be the major beginning of finding all this. Then A goes from the center up to and down to the vertices, or here. So the whole major axis would be 2A, and then B gives us how we get to the kind of the sides of the ellipse. Okay.
Which one is the major and which one is the minor axis?
The major is the longer one. The major is 2A. The minor will be the 2B. Okay. And then the equation to find C, which gives you the foci, to find C, we'd have A squared minus B squared. Okay. And the foci will actually be a little bit inside the vertices. In the ellipse, A will be bigger than B and C. Okay, the hyperbola, we can't say anything like that.
A is going to be bigger than B.
A is going to be bigger than B. A is going to be bigger than C for the ellipse.
Which?
So the hyperbola looks very, very much like the ellipse, except we have a minus here. And A squared will always be on the positive term. Doesn't necessarily have to be bigger than B this time. But this one, just a kind of a quick sketch. If that's our center, HK, then our hyperbola is going to open left and right. A is still, just like the ellipse, still from the center to the vertex. And the focus this time is going to be larger than, or outside the vertex. So C this time is bigger than A. Okay. But we cannot say A is greater than B. Sometimes it is, sometimes it isn't. A is always going to be the denominator of the positive term.
To find the focus, wouldn't be
To find the focus, from the center we go out C. Well, C squared this time ends up being A squared plus B squared. Okay. So again, make sure you get all these formulas written down and straight, and make sure you get the right equation with the right conic section. And for the B value in graphing this, I'm not going to have you find the equation of the asymptotes, But if you're to graph this, we go up B and over A. Well, my little trick is just create a little rectangle, 2A on one side and then 2B on the other side, and then your asymptotes go through the center and through the corners of that rectangle. So I'm not going to have you find the equation of asymptotes, but at least be able to graph it. If you want to put the equation of the asymptote down, fine, but to me, the only thing I'm going to worry about is the graph. Okay, and that's for the horizontal transverse axis. The vertical transverse axis, that's going to have the y as the positive part minus the x part. And again, A could be bigger, A could be smaller than B. So that would be the vertical transverse axis. And in this case, transverse axis is 2A. Just like the major axis in the ellipse is 2A. Transverse axis goes from one vertex to the other vertex through the center. And this time the foci would be up and down from the vertex. Okay, questions there? So like I said, the problems that will involve the conic sections, given an equation, maybe find the vertices, find the foci, find the directrix, find the focus of a parabola, or given characteristics about the conic section, find the equation and graph it. Now, on any of here's the equation, give me characteristics about it, you may need to go through the completing the square. So you've probably done enough of those by now. It's old hat, but that's a possibility. Rewrite it to this form. I don't think I'll be nice enough just to give you directly that form. So. And that'll cover probably 3 or 4 problems. We spent quite a bit of time on that, and so be a decent portion of the test. There will be 13 problems total on the test. So 3 or 4 of the conic sections. Then we move on into 10.2 and 10.3 with the parametric equations. And with those, we looked at a lot of, just the basic idea of what are the parametric equations, graph something using the parametric equations, find the derivative, so what's the formula for dy by dx? dy by dt, or dy by dx, sorry, would be the derivative of y with respect to t divided by a derivative of x with respect to t. And then that finds what for our graph?
On the arc length?
Well, we use that for arc length, but before that, what does dy by dx represent on a graph?
Tangent line.
Okay, slope of the tangent line. Okay. What about the second derivative? First of all, the formula would be what? Well, this looks strange, but this is how we do it. It would actually be the derivative of this with respect to t divided by dx by dt. So got to find your first derivative, then take the derivative of that in terms of t. That would be your numerator, and then divided by dx by dt. Kind of looks strange when you do that, but now second derivative from a graph tells us what? Okay, concavity. If the second derivative at a certain point is positive, then the curve would be concave up. If the second derivative is negative, curve's concave down. So at least we're kind of getting back to some of the easier stuff from Calc 1, some of the things you hopefully remember. Back finding our first derivative, we can also find where we have horizontal tangent lines or vertical tangent lines to those curves. And it's fairly straightforward. Turns out to be where dy by dt equals 0, where the numerator equals 0, that's going to give you the horizontal tangent lines. And vertical tangent lines, well, vertical lines have undefined slope. Well, that comes from the denominator equaling 0. So horizontal and vertical tangent lines, where do those occur? It's essentially taking your numerator, setting it to 0, take your denominator, set it to 0, and then don't forget, that'll give you the t value. Plug the t in to x and to y to find the point. So, questions there? Another thing we looked at with parametric equations, find the arc length from one point to another. And what's the formula for that? Integrate from t equals a to t equals b. Square root of dx by dt squared plus dy by dt squared. Okay. So again, using the dx by dt and dy by dt, and that looks fairly similar to our arc length of a y equals f of x, but using the parametric equations. Questions there? And like the arc length with y equals f of x, sometimes the integration is ridiculous. Sometimes it's difficult, if not impossible, to do. So something like that, I may just say, set up the arc length integral, do not evaluate. So I won't make you go through the ugly algebra part. And again, some of them are impossible to do anyway. But
You can, but
well, they would be possible to approximate in some cases. Some cases you could find the exact value, but you'd have to go through some really interesting integration techniques.
interesting.
Yeah, interesting. Good word. Okay, then we throw polar coordinates at you. And the main thing there, thinking about the conversions instead of going here's x and here's y, well, somebody came up with the interesting idea, let's call this point R and the angle theta. So the conversion's not too bad to work with. This is x, this is y. R is simply the hypotenuse. So R would equal square root of x squared plus y squared. And then theta, well, tangent of theta would be y over x, or theta would equal arctangent of y over x. Or, in terms of x, or what the polar coordinates are in terms of x and y, well, that's just by the definition of your sine and cosine. X, well, cosine of theta would be x over r, so x is r cosine theta. Y would be r sine theta. So make sure you have those formulas written down, or at least know how to find those formulas. I may have you convert a rectangular point into polar coordinates, or might have a polar point convert to rectangular coordinates. We did some conversions, whether it's points or whether it's equations. Make sure you know how to do both of those. Another problem that we ran into was the slope of the tangent line. Now, it gets really confusing to me when they throw this in the general formula. What I have to think about, let's say r equals 1 plus sine theta. To find the slope of the tangent line at a certain point or at a certain value, well, you've got to find dy by dx, but we've got to use the parametric equation idea. We take r and substitute it in here, and we'd have x equals 1 plus sine theta times cosine theta, and y r times sine theta. And then from there, we have x and y both in terms of theta, and we run through the derivative using parametric equation idea instead of the polar coordinates. It gets kind of long and drawn out, but to me it's a lot easier to think of it in these terms rather than look at the formula they develop in their video. It works, but it's confusing to me. So, okay? Question on that? And then 10.5 worksheet, we looked at finding the area of a region given in polar coordinates. And some of it was find the area inside a curve. Some we looked at find the interior of a certain curve, or some of these, they're called the rose curve. Let's see, am I graphing that right? Maybe. I think that is r equals sine 3 theta, maybe? Something like that. sine of something theta and cosine of something theta will give you the what we call the rose curve of so many petals. It's funny that it depends the number of petals. I think the sine curve is exactly what this is.
Yeah.
Cosine, it's like
There's
2 times that value. Weird how that works out. But problem for these petals, find the area inside one petal. Okay. So instead of finding the entire curve, let's find the inside one petal. And that would be basically figuring out what the integral limits will be. So theta 1 to theta 2. And that kind of takes some work with the polar coordinates, but it might go from 0, well, in this case, I think it's 0 to pi over 3. Yeah.
Yeah, I think it's part three.
I watched the video.
So, yeah, it might help to watch those videos.
Yeah.
But, yeah, I think 0 to pi over 3 would get that.
Man, I got it.
Now, cosine is a little trickier because a lot of times cosine starts here. R equals cosine 3 theta. We'll just throw that one in there. Well, if theta is 0, R is going to be 3. So this one, you go from 0 to pi over 6, I think will get you back here. That's only half a petal. And then it kind of goes, let's see, which, I can't remember exactly how it sketches out, but 0, starting at 0, won't get you the full petal with the cosine. So you got to figure out, well, what's this? And if I'm remembering that one's, I think it'll kind of go maybe like that. So one way to think about it, you got to find what the angle is, what theta is getting here, and then to get back there. So maybe it's pi over 6 to pi over 3 will be from one edge of the petal to the other. So, and as we also work with polar coordinates, what's our dA? Remember? How do you find, is it just r d, or the function times d theta? Okay. That's how you're going to need to set up your polar coordinates. So a little different than the rectangular, a little more work to it. But that would give you the area of f of theta from one angle to the other angle. Okay. Now, once in a while, you get some pretty crazy integrals. These aren't too bad, but with the trig functions, but I will allow you to use the integral tables. So you still have those, right? I'll make sure and bring some copies just in case, but your integral tables will be allowed as well as your one sheet of paper. So, okay. Let's see. Probably the last part of this, last part of the worksheet gets a little trickier when we start looking at area between two graphs, or area between the outer side and the inner side of a graph. 10.5, number 21, for instance, says between the loops of r equals 1 plus 2 cosine theta. Now, I don't know exactly how this graphs out, but something like this. Sometimes you'll see the graph like this. So it's a matter of, well, what is this area? Not all of it, but inside the big loop and outside the little loop, we're not counting that area right there. So you've got to figure out a way to find that area. Maybe it's do the whole thing and then subtract out the inner loop. Maybe you can find where the outer loop starts, like theta is pi over 4 to 2 pi, or it all depends on what the combination is and what happens when theta equals 0, where does it start. But those get really interesting, and there's a lot of analyzing that you have to do to figure those out. There's more than one correct way to set it up as well. You might find it easier just to go from 0 to 2 pi, get the entire area, and then subtract out the area of the little loop. So, or, like I said earlier, figure out what the theta is for the outer loop around to where the outer loop ends and find that area. So several different correct ways, but make sure you look at those. Might be a problem like that. Okay. Questions? Yeah, good question here on how do we figure out the angles where one pedal starts and where it ends. A lot of time it's probably just as easy to look at plot some points. Something like the r equals cosine 3 theta. Like we said, if theta is 0, r will be 3. What we're really wanting is to find when r is 0. And in this case, well, the first place where cosine equals 0, cosine of an angle equals 0 would be what?
Pi over 2.
Yeah, right, pi over 2. So that would be saying, so theta would be pi over 6 to make r equal 0. So that would be a good starting point for that one. So that would be here. But then how do we figure out what loop? We kind of have to, again, play with some values. Might be where's your next spot where cosine is 0. And that would be at 3 pi, let's see, 3 pi over 2. So 3 theta equals 3 pi over 2. So theta would then be pi over 2 to get to our next one. So kind of, again, that's just one of many ways figuring out what the limits are, but that might be the easiest way, just to kind of guess and check. And there's a lot of thetas that will give you 0. We just have to kind of methodically say, okay, if this is the one we're looking at, then how do we get to the next one? But that would be a good way to look at it. Any other questions?